Hello everyone, my name is Kathan and today we'll be discussing the problem Mex Grid Construction from the Introductory Problems of the CSES Problem Set. Let's begin. Let me read out the question for you. A task is to construct a n by n grid where each square has the smallest non-negative integer that does not appear to the left on the same row or above on the same column. And our input is simply an integer n and we have to output the grid according to the example. Now, what does it mean according to the example? A given cell value, let's say here 1, what this says is you have to spit the minimum number that is not present left on the same row and you can say top of the same column, right? So a grid value ij is actually, you can say, this operation. This mex is actually called an operation, minimum excluded of all the values to the left of it and all the values to the top of it, right? So you take all the values to the left of a guy, all the values top of the guy, and find out the mex of it. That is, find out the minimum excluded number in this set, and that will be the value of grid ij, right? So this mex operation is a very common operation in competitive programming. You'll see it a lot of times. So it stands for minimum excluded. Don't worry, I'll take examples. But the idea is, what they're asking is, you'll be given this n, which is a positive integer from 1 to 100, and you have to split a grid, which is an n by n grid, such that a value ij gives you a mex of all the values before it on the same row and all the values above it on the same column, right? So for example, this 1, how is this 1 coming? What are the values just before it in the same row? 2, 3. What are the values just before it in the same column? 0, 2, 3. So 0, 2, 3 and 2, 3. So what is the minimum value that is not present in this set? It is 1, right? Because if you have a sequence 0, 1, 2, 3, 1 is, you can say, if 1 is missing, that is the smallest value which is missing from this sequence, right? So don't worry, I'll explain the mex operation one more time. But that's the question, and there's one more thing. You can look, the constraints are pretty less. So it says that you can maybe run a brute force, right? So if the constraints are high, maybe you have to think a bit better, but constraints are low, so there will be some sort of brute force can work. That's what it says. So I mean, yeah, let's go to the iPad and try to understand this question a bit more. First things first, let's talk about this mex. Like, what is this mex operation? Now, this is a very common operation that you will encounter in competitive programming. So I want to spend some time here and build the intuition for it. This mex stands for minimum excluded, right? So for example, if you have a set, let's say the set is 1, 2, 3. So what does this minimum excluded say is, you spit out the smallest non-negative integer not part of this set. What is the smallest non-negative integer not part of this set? Non-negative means greater than equals to 0. It is actually 0, right? For example, let's say you have a set like this, 0, 3, 4. So what is the smallest non-negative integer not part of this set? So the non-negative integers are 0, 1, 2, 3, so on, right? The smallest non-negative integer is 1. So the output here is 1. So I guess you got the idea of what is a mex operation. It simply stands for minimum excluded. You just spit out the minimum excluded guy, like you can say minimum excluded guy in this set. Smallest non-negative integer not part of this set. Now that's about that. Now let's just go through our matrix and try to make some observations here. Like, what do you see? Now this value here, so I'll just go through a value and try to make you understand what is happening. So this value 5 here, it is actually mex of these guys, right? It's the minimum excluded of 1, 0, 3, 2 and 4. So what is the smallest non-negative integer not part of this set? It is actually 5, right? Because these values are 0, 1, 2, 3, 4. So the smallest non-negative integer not part of this set is simply 5, right? So yeah, I mean, let's take one more example then. Let's say this 3. So how does this 3 came? Okay, not 3. Let's just take this 2. So this 2 turns out to be the mex of all the values above it in the same column and all the values left of it in the same row. So what is the mex of it? So I'll write the values here. Mex of 0, 1, 3, right? So 3, 3 same. So don't need to write it again. So what is the mex of these values? So you have integers from 0, 1, 2, 3, so on. So the minimum value which is missing is 2. Hence the value 2. So I guess you got the question. The question is grid of ij has to be equal to mex of the set. And how do you define that set? That set is defined like this: grid of 0 I minus 1 j, 0 grid of I minus 1 j, and this is one set union. I can write it here: grid of I 0 till j minus 1. This is simply all the guys on the left of it on the same row and all the guys on the top of it of the same column, right? So this is just a fancy way of writing it. Fine. So what do you see here? Like, let's try to make some observations and see if we can solve this question. Now, one thing straight away grabs your attention is all the diagonal values are 0 in this grid. So II is 0. Right, so for convenience sake, I've also written the indices here. Maybe if we can get some idea from the indices as well. So maybe these indices are related to these values, right? So firstly, II is 0. That is, all the diagonal values are 0. Then look at this 0th row. It has values like 0, 1, 2, 3, 4. For example, if 0 is associated with all the possible columns, you get the column number back. In other words, for the 0th row, you get the column number back, right? For example, 0 with 0 gives you 0, 0 with 1 gives you 1, 0 with 2 gives you 2, so on and so forth. Similarly, for the first column as well, you can see if you pair up any row value with the 0th column, 0 with 0 gives you 0, 0 with 1 gives you 1, 0 with 2 gives you 2, so on and so forth, right? So I0 also gives you I. Fine. What else do you see? Rest all thing is fine, right? So rest all cells are property in the Mex property that I've written here. Now, if you know a little bit about binary numbers, or you can say the bitwise operations, just by looking at these operations, something should struck in your mind that you know that if you XOR two same numbers, the output is 0, right? So this is a property of XOR. So this plus dot is actually the XOR I've written, or sometimes people write it like this. Like this is the XOR operator in C++, but like this is how you use it in notation, algebraic notation. Fine. So XOR X is 0, fine. And these two should directly tell you, you should remember, relate it, that X XOR 0 is X. So you XOR anything with 0, it returns the same value. And if you XOR two same values, you get 0. So it gives you a hint, is the grid value ij, is it just I XOR j? Right, I'm just making a claim here. Is it the case here? Let's see, let's try to see some values and then maybe we can prove it. Fine, let's look at a value here. Let's look at this guy. So of course, this is true for first row, first column in the diagonals, because by the property of XOR, if you XOR anything with 0, you will get the same value. So it is of course true here. And by the property of XOR, if you XOR same elements, that is 0 XOR 0, 1 XOR 1, 2 XOR 2, 3 XOR 3, 4 XOR 4, it will be 0. So diagonals and the first and first column are automatically verified. Let's see some more values here. Let's take this value 2, 3. Right, so let's try to do XOR of it. So if you don't know the properties of XOR, they are like this. So 1 XOR 0 gives you 1, and 0 XOR 1 gives you 1 again. 0 XOR 0 gives you 0, and 1 XOR 1 gives you 0. So if you have odd number of ones, then the value of XOR will be 1. And if you have so that's the thing. If you have odd number of ones, the output will be 1, otherwise it will be 0. Fine. So let's take this 2, 3, right? So what is the binary of 2? So the binary of 2 turns out to be 0, 1, 0. And what is the binary of 3? Binary of 3 is 0, 1, 1. So if you take the XOR here, 0, 0 will give you 0. Then 1, 1 will give you 1. Sorry, 0. And 0, 1 will give you 1. So eventually, the value, the grid 2, 3 is actually 1. Fine. Let's take one more value. Let's take this here, 4. 4 will be straightforward. So let's take this value here. This is actually 3, 1. So 3's binary is 0, 1, 1, and 1's binary is 0, 0, 1. If you take 1 XOR 1, it is 0. 1 XOR 0 is 1. 0 XOR 0 is 0. So this again comes out to be 2. Fine. So you can verify it for yourself by taking more examples. Grid of ij, like here, in every one of them will actually be equal to I XOR j. So can you conclude it? Right? Because if you can conclude it, the question is done and dusted, right? You can just run a loop for I equals to 0 to n, for j equals to 0 till n, and just print I XOR j. Right? So the question is done and dusted there. But we have to prove, right? We have to prove that this is actually the case. Because by looking at this matrix, all the values here are definitely I XOR j. but we have to definitely prove it. So for now, let's just assume we are trying to prove it, right? So what I'm trying to prove here is grid of ij is actually equal to, you can say, the max of all the values before it on the same row and all the values above it on the same column, right? So in other words, I'm trying to prove this value is equal to I XOR j. Now we are going to prove it using a very important method, proof by contradiction. So let's assume that we have a k less than j such that I XOR k is equal to I XOR j. So what I'm trying to say here is you have a cell here ij, right? You have a cell here ij. I'm trying to say that I have a k here on the same row, that is one of the columns here is present such that if I XOR the row number with it, I'm getting I XOR j. In a way, I'm saying that this cell value cannot be I XOR j because I XOR j is already occurring in this row to the left of it, right? So I'm saying I XOR j cannot, like this value cannot be I XOR j, a cell value cannot be I XOR j because this value is already occurring on the left of it on the same row. That's what I'm trying to say, right? So this I XOR k is equal to I XOR j, right? On the same row on the left of it, I already have this value, so you cannot have this value. So this is my assumption basically, right? So that's how proof by contradiction works. You assume something and then you reach to a contradiction and you say your assumption was wrong, right? So that's how it is. So here I'm assuming that on the same row to the left of it, I have already I XOR j present. Okay, fine. Now what next then? You have this inequality here, this equality here. Now let's take XOR of I on both the sides. If you take XOR of I on both the sides, what you get is you get I XOR k XOR I, and you get I XOR j XOR I. Now there is a property of XOR. XOR is commutative and associative both. So A XOR B is actually equal to B XOR A, and A XOR B XOR C is actually equal to A XOR B whole XOR C. So this is commutative, this is associativity. So this I guess you have studied in your +2 or 10th, whatever. So commutative and like associative property. So you can just rearrange these terms here and you will get this I XOR with I. So this will become k, and so I XOR I will be 0, and here also this I can be rearranged and XORed together. So I XOR I will be 0. So you'll be left with 0 XOR k equal to 0 XOR j. So 0 XORed with anything which returns the same value, so this becomes k. So k is equal to j. But here's the contradiction. I already assumed k was less than j. So this is, you have a contradiction because you already assumed that this k was less than j. You were trying to find this I XOR j on the same row to the left of it, but you didn't find it. So you can say this I XOR j doesn't exist on the same row to the left of this cell, right? On the same ground, so like you can assume a k which is less than I, right? You can assume a k less than I and you can try to prove it. So you'll get that, so this is a proof that you cannot have I XOR j on the same row to the left of it. Now on the same ground, you can assume a k which is less than I, and prove it that you cannot have I XOR j on the same column itself. So I leave that as an exercise for you, but it's basically the symmetric proof of this. Fine. So what you effectively proven is grid of ij is equal to I XOR j. Right? You cannot have this value before it. So this value is unique, right? But how do you prove that this is actually minimum exclusive OR? Right, so this value is unique definitely, that for example this value will never occur here, will never occur here. This value will never occur here, will never occur here. So it will not occur on the same row to the left of it, and it will not occur on the same column on the top of it. But how do you prove this is minimum? Now this minimum thing, it is bit, you can say, a trivial thing. You can just observe that for example for the 0th row it's obvious. If you have 1 here, now you know that this 1 is unique. There won't be 1 here. There won't be 1 to the left of it, which hinders the Mex construction, right? For example, if you are not sure that this guy I XOR J is unique, that is if it is occurring here or here, then the max won't be equal to this. But at least now you are sure that this value doesn't occur here and doesn't occur here. So this can be the max. Now how do you prove whether this is actually the minimum excluded? Now this just comes by the nature of how XORs work. So you can just see here, if you see this value, there is 2 3 here, there is 2 3 here. So definitely the max is 0 here, right? For example, if you see this 1 here, you have 0 2 like 2 3 0 here, you have 3 2 here. So by definition this becomes 1, right? So the way you fill this matrix, for example, even if you look at the 6, you have 0 1 2 3 here, 4 5 here. So by definition this has to become 6. So the minimum part is, but you can say trivial, or the way XORs work, you are getting that part. But the important thing was grid ij is actually unique, and if you get this value to be unique, that if you are sure that a grid value, this cell is unique in a way it doesn't occur here and here, just by looking at it, the way this matrix is formed, we can see that this value will be minimum excluded of this and this, right? So you can extend it. For example, this is 0. Why? Because you have 4 5 6 7, you have 4 5 6 7. So of course the minimum excluded is 0. This is 1. Why? Because you have 2 3 here, you have 0 2 3 here. So definitely 1 is missing. So that's the idea. So I mean, yeah, the question is done and dusted. I hope you have got it right. So if you did get the explanation, like, please comment understood in the comment section of the video right now, and let's go to the code part. Alright, so the code is pretty simple, right? You take the input n and you just print I XOR j for a given, like grid ij is equal to I XOR j, and fine. The time complexity is simply order of n square because you are iterating the grid once. Space complexity is order of 1 because you are not using any extra space. And that was the video, guys. I hope you liked it. If you did, like, please give a thumbs up. And I have one exercise for you. Like, n was pretty small here, right? So maybe you can just implement the brute force. How are you going to implement the brute force? That's an interesting thing. Let me know how are you going to implement the brute force then in the comment section. Fine, then I'll see you in the next one.